Let's next take a look at the inverter and the switches. The summer and the pots will allow us to sum the noise canceling signal with the music. But since the summer also inverts, we won't need another sign change to do the noise cancellation. Now there will also be a sign change to the music. And what this represents is basically a time delay for all frequencies. So when you listen to the music, you won't notice the fact that everything's been delayed by a fixed amount of time. We still do need one more sign change. To get the eavesdropping option, we need to have no sign change on the picked up signal. So we'll need to add a sign change to this to cancel the sign change in the inverting summer. And we could do that with an inverter. Take our signal coming off of the non-inverting amplifier and just feed it to the summing amplifier, we'll get a sign change. If we pass this through a gain of -1 and then send that to the summing amplifier, we'll get an additional sign change, and that'll cancel the sign change of the inverting summer. And we'll be able to pick up what's picked up by the microphone in the headpiece. One of the hard parts about designing a circuit is actually picking the component values. Now there are a lot of non-ideal effects of op-amp circuits, and we'll touch on this in ECE 402. But what I can do is give you some rough guidelines to help you pick resistors to kind of minimize non-ideal effects. As far as resistors go, if you pick them between 1 k ohm and 1 million ohms, you won't see much of the non-ideal effects of the op-amp. The reason I picked a resistor around 1 k or more is that if you picked a small resistor, say 1 ohm, and you had 1 volt across it, you're looking at 1 amp. Op-amps can't provide that kind of current. They're typically limited to around 20 or 30 milliamps. So if you had 1 volt across 1 k, you're looking at 1 milliamp. Resistors actually generate noise proportional to their value. So when you use larger resistors than this, it can create noise in a circuit because of the gain of the op-amp and effectively a noise voltage source associated with the resistor. So if you stay below a megohm, generally you won't notice the effects of the noise of the resistor. Picking some components, sometimes you have to go to lab and take some data before you can actually pick a value. This was the case with the microphone. So I need a plus and minus power supply to operate the op-amp. Suppose we use plus or minus 9 volts. We could use 2 9-volt batteries, or we could use the power supplies that are in lab. Most microphones need about 500 microamps of DC current to operate the field effect transistor in its active region. But this depends on the model of microphone that you have. So I went to lab and took some measurements. So I used a 9-volt power supply, and then I used a 4.7 k resistor for the biasing, and measured the voltage coming out of that microphone circuit at about 7.5 volts DC. Then I spoke into the microphone, had approximately plus or minus 1 volt variation. So I went up about 8.5 volts and down to 6.5 volts. Basically things work. I could play with this resistor some more, but as long as I can get my AC signal with a DC level on it, I'm going to block the DC level. Let's next pick the component values for the audio frequency non-inverting amplifier that was on page 7. The corner frequency was at 1 over 2 pi R1C1. I'm going to pick that to be around 20 Hertz so that I can pass the entire audio band. Now the amplifier that was built into the microphone still will need some more gain. As we saw that when we spoke into the microphone that we got out about a plus and minus 1 volt AC signal. If I gave that a gain of 4.5, then that means I would swing a plus and minus 4.5 volts, and this is about half of our power supply. That would leave us a little bit more for the remaining stages of gain. Well, given that information, we can start to pick the resistors and the capacitors. Suppose we pick the resistor R1 in the audio frequency non-inverting amplifier to be 1 k ohm. Then to get a gain of 4.5, we would need R2 to be 3.5 k, because the gain is 1 plus R2 over R1 once you get past the corner frequency. The nearest standard component that we have in our parts cabinet is 3.3 k. It's going to give us an overall gain of 4.3. Given we pick the value of R1, we can now solve for C1 from the fact that 1 over 2 pi R1 C1 should be around 20 Hertz. Putting the C1 here and the 20 over here, we get 1 over 2 pi 1k times 20 Hertz, and that's about 8 microfarads. Our nearest value in the parts cabinet is about 10 microfarads. And we also have a constraint on the product of C2R3 with C1 times R1 plus R2. This is really a pole zero cancellation. Now we picked C1 to be 10 microfarads, R1 is 1k, and R2 is 3.3 k, so that product is 43 times 10 to the minus 3. If we pick C2 to be 0.1 microfarad, again a standard value in our parts box, then we could solve for R3. It would be 43 times 10 to the minus 3 divided by 0.1 microfarad, and that's 430 k. The nearest standard resistor is 470 k. This is a factor of 100 times bigger than the biasing resistor we picked for the microphone, which is what we'll see as the frequency increases and we short out the capacitor C2. So we have a high enough input resistance not to load down the microphone circuit. Next, let's pick the resistors for the inverter that was shown on page 9. Here the ratio of output to input is equal to -1, so we need to have 2 equal valued resistors. Here we can pick anything. Let's pick again something between 1k and 1 megohm. I'll pick 10k because it's a standard resistor value in our parts cabinet. Next, take a look at the summing amplifier with the variable gain that we did on page 4. You have to pick the value of the potentiometer. Let's say pick it to be 100K, it's a standard value. Then my value for R1 is the pot divided by 10, so that I can get a linear rotation with power as I'm moving the pot from one end to the other. So that gives me a value of about 10K, which again is also a standard value resistor. Now the non-inverting amplifier boosts the largest microphone signal that I had to about half the power supply. So this last stage of gain, I would have to have a gain of at least 2 to get to the full swing of the power supply. But I found that there were some issues with smaller signal levels. In lab, I played with gains from 2 to 10. When I had a gain of 10, I noticed that there was squealing in the headphone. What was happening is that some sound was coming back from the microphone back into the headphone and then getting amplified again and amplified again and amplified again. So I wound up playing with other gains, and 3 or 4 seemed to work pretty well. Be able to do the noise cancellation without getting the squealing. You could also modify this in lab if you find when you're testing yours that things are slightly different. So I'm going to get a gain of around 3. I can pick a 33K resistor, and then with my 10K resistor, that'll give me a gain of about minus 3.3. Let's next take a look at trying to generate a low noise system. Noise in electronic circuits is a subject that we treat in ECE 402 and 404. It's quite complicated, and it's way beyond what we can cover in ECE 203 and in 202. But what I can do is give you some good practice guidelines so that when you're designing your circuit, we can have an overall low noise system. In ECE 402 and 404, we'll be able to calculate as well as measure circuit noise. As we mentioned previously, one way to reduce noise in a system is to use low-valued resistors. Low value being less than 1 megohm. Then the noise generated by the resistor will be small enough not to be noticeable in the system. Another thing to do is to use a low noise op amp. Op amps contain transistors and they also generate noise. Some integrated circuits are optimized to reduce their noise generation. In this lab, we're going to use a NE5532 low noise op amp, which is one of these devices. The noise that's generated by this op amp is about a quarter that of an LM741. Another thing that contributes to noise is the overall bandwidth of your system. Again, we'll learn how to do calculations in ECE 402 and 404, but for right now, the simple idea of just simply limiting the bandwidth of your circuit to the audio band will minimize the overall noise that you hear. As you saw on pages 8 and 11, the lower end of our system bandwidth is about 20 Hz. Now, if our op amps were ideal, the upper end of our system bandwidth would be very, very high. But this particular op amp, as well as every other non-ideal op amp, has an upper limit based on a thing called the gain bandwidth product. We'll learn how to calculate these things in ECE 402, but for this particular op amp with the gain that we've selected, the upper 3 dB bandwidth is about 2.3 megahertz. Now that's much more bandwidth than we actually need because we can only hear up to 20 kilohertz. So what we need to do is to lower the system gain with frequency. One way we could do that is with a capacitor because its impedance decreases as frequency increases. If we put this in parallel with the resistor R sub F, as the frequency goes up, that parallel combination's impedance will go down. What I want to do is pick the value of C sub F so that my 3 dB point would be equal to 20 kilohertz. For V1, we have a gain of minus Z sub F over R1, where Z sub F now is the parallel combination of a capacitor C sub F with the resistor R sub F. So I'm going to add their admittances and then take the reciprocal to get the impedance. Multiply numerator and denominator by R of F, and I get R sub F divided by 1 plus S C sub F times R sub F. Pull out the R sub F, then we have left over 1 over 1 plus S times C sub F R sub F. If we do the same thing for the other input V2, we'll get the same result but with R1 replaced by R2. Let's again plot this transfer function using the Bode plot techniques in chapter 12 of ECE 202 on pages 3 to 11. Again, I'll leave this as an exercise for you to do, but here I've got 2 dotted lines that are going to approximate the magnitude of the gain versus frequency. And the value at low frequencies, the magnitude is R sub F over R, where R is either R1 or R2. This is a plot of the phase angle of the gain from low frequencies to high frequencies. And it starts out at 180 and eventually goes to 90 degrees. The corner frequency is at 1 over 2 pi R F C sub F. We want to limit our upper 3 dB bandwidth to 20 kilohertz because that's as far as we can hear. And also give us the lowest overall bandwidth and will actually give us the overall lowest noise. Since I know the value of R sub F, I can solve for C sub F from this equation. So C sub F is equal to 1 over 2 pi R sub F, which is 33K, times the 20K. That gives me a value of 241 picofarads. The nearest standard component is 240 picofarads. And now we finish our design. Let's take a look at the final design on the next page. Here's our entire system drawn out. We start out with the output from the microphone on the right and left channel. Comes in through a capacitor, blocks the DC, both of these. Sees a fairly high input resistance compared to this, so we don't see much loading effect. Then we have the gain of 1 plus the resistor ratio when the frequency is high enough to make this a short circuit. Of course, the same thing's happening on the left channel. Okay, then we come to this switch. When the switch is in the up position, we connect from here to here, and likewise from here to here. And that bypasses the inverting amplifier, takes us to a potentiometer that then feeds one of our summed inputs. Same is true on the bottom here. We bypass this, feed it to a potentiometer, then feeds one of the inputs of our summing amplifier. On the bottom, I have two auxiliary inputs, one for right and left channel. This would be another source of sound. Again, through a voltage divider, and then fed into the summation for the two channels that we have. Now suppose we flip the switch in the other direction. Then we connect this to this, and this to this. And that just takes our signal from our non-inverting amplifier through a gain of -1, and then fed back into our system. Likewise on the bottom, as you go through here, back into our potentiometer. Then we get a sign change, and that nulls the sign change of the summation. And then these two outputs go to our headphones. The purpose of this lab was to design some noise-canceling eavesdropping headphones. This lab had some new concepts, but no new measurement techniques. What we learned about was bandwidth limiting to reduce noise, using low noise op amps to also reduce noise. We're going to use what are called gang pots, which are two potentiometers on the same shaft, so we can adjust both the right and left channel to vary gains simultaneously. We're going to use the double pole, double throw switch to change from noise-canceling headphones to eavesdropping headphones. There's a lot of myths about noise-canceling headphones, and so we're going to be able to test in lab and be able to check out some of the ideas of noise cancellation. In particular, by playing with different frequency ranges, we can see what ranges of frequency we actually can cancel and which we can't. Now, this is a 2-week lab. The first week that you come, there'll be a quiz on the background material, which includes these notes, the video, and then also the lab procedure. For the second time you come, there won't be a second quiz. And this is lab number 6, noise canceling and eavesdropping headphones.